Welcome to the Delta Elevation Controller. With this prototyped design, we have a proof of concept of an elevator control system. Let's get into the specifics. So why am I doing this? Well, I'm doing this to integrate mechanical and electrical controls into a unified elevation system. So this is to be able to actually have the microcontroller computing to real-world devices to be able to fine-tune critical systems and the overall operation of this device. And of course, for learning experience. And also, I'm doing this to get a better understanding of HMI screens. So developing my own HMI screen was very important to me, and to be able to repurpose that to other devices that display important information about its operations and life cycles. And next, it was to learn to incorporate various components, electronic components, such as microcontrollers, Hall effect sensors, this little guy says shift registers, and even DC motors and stepper motors and such. So the mechanical components were quite a bit. There was a lot of designing involved and a lot of iteration. So I used a lot of 608 bearings. These were used for keeping the elevator car stabilized in the proper position, as well as keeping the actual counterweight device that goes up and down from tilting and rotating and hitting into the car. And then also it was used for the gear train or the gearbox to be able to rotate the various gears and step it from 10 to 1. And that was very important to keep everything nice and tight. Next, we have the T-bar guide rail. So basically, I am using a T-rail. If you excuse me a second, I'll go grab it. Okay, I'm back. Sorry for that little jolt. So basically, this is a T-rail, and it just goes on the inside of the elevator car, and a bearing is fixed on one side. I mean, you can see it like this on one side and on the other side, and it basically just pinches it, and that's used to guide it. And another one is pushed forward in with it's a cam, so it's spring loaded, and that helps to keep the elevator from going tilting towards one side or the other, and the other one is to prevent tilting from the front and back. And essentially that is used to keep the elevator going in the proper orientation. Next, I actually am going to be incorporating little contacts on the rail, so when the bearings run over the contacts, we'll use that as a redundancy for the limit switches, as there was some issues I'll get into later about the limit switches. So next we use a 10 to 1 gear train ratio. So I'm basically stepping a 24 teeth over to a 48 teeth, and I believe it's to a 60 teeth, then to 100 teeth, and I step it a couple more times, and then I end up on the other side with an actual spool, and the spool has a little radial slot carved out or cut out, and that's where our cable runs, and it uses friction and goes around 3 different spools, and the friction is what helps pull the elevator car up and down. Next, it is mounted with the mounting motor is mounted with seated bearings. So basically, there's some bearings that are actually incorporated not only in the where it's installed on the roof of the shaft, but it's also actually inside the motor block as well. So there are some through holes that support it, and that's because I have to go from one side of the mounting block across with a shaft to the actual spool section that holds the wires. So running across, I stabilize with 608 bearings in between, and I have a shaft run through, and it's actually a one piece, and it goes together. Next, we have the elevator car cable suspension. So basically using 0.8 millimeter steel wire that's coated with plastic, I think PVC, black PVC. And essentially it's just being carried through those spools and attached to a counterweight, and also it is attached to the elevator car. And that elevator car is actually attached to a load cell that's attached to the elevator car, and we use the load cell to detect the weight. Now, was there design challenges? There definitely was. There was way too many design challenges. So one of them was parametric issues. So I had designed in an assembly, and I guess I had designed in such a way that changing one detail in one file actually changed the size of a lot of the key components, like the walls and the elevator itself and the motor mount. So everything got kind of wrecked, and I couldn't figure out where the change came from. So I actually had to refactor a lot of the files and redo it, and this is because I was being a bit careless and rushing, because I was just trying to make a proof of concept, and the concept of not sleeping enough and doing good quality work at the onset is proof of these things. Okay, so then there was also issues with the tolerancing in the 3D printed holes. So depending on the material I used and the amount that it was dried, the speed that I printed at, and the nozzle size, I did notice there was some issues where if I were to give about 0.3 millimeters clearance for shafts and holes, there still wasn't enough room, and in other cases there was. So there was some reprints that were needed to be able to figure that out. And then also I was building components as there was a need case. So for example, the button that's in the bottom, the electrical stop, excuse me, thank you. Sorry about that. The electrical stop itself was used in the basement to be able to position, because I was positioning with limit sensors, and then I decided that was a little bit cumbersome, so I just printed it apart as I went. And different supporting parts to make everything more sturdy was designed as I went as well, and as well as a couple other parts like the cam to hold the elevator into the proper side-to-side positioning. So next we have the electrical components. So first we use limit switches up here, and those were used for positioning. There was a problem with that though, that the limit switches were designed to be actuated in a single linear direction, and the reverse direction created a high probability of bending and damaging and not working properly. So that is why I had mentioned on this T-rail about putting permanent contacts in the rail instead of relying solely on limit switches. So the other point is that I may redesign the limit switches through 3D printing, or try to outsource them from a supplier where they are. So basically it was like a block, and then it had an arm on it, and the arm has a wheel, and when you come this way it rolls against the wheel and pushes it down. But the problem is, let me just hold it like more like this, if it comes this way it might actually get it the wrong direction. In this case, it's always down, but in this case, it could bend like that. So having something where it's like, a triangle, and in both directions it can catch and deflect up and down would be better. So I'll do something like that, or purchase something similar to that. And I also think I might be just solving the problem by putting them in here. I just need to figure out the tolerances for the wheel, because this is quite thick for the tolerances to fit wires in there. So I'll need to just kind of sort that out. Next, I use shift registers. So these are basically a way to expand my outputs without using expander boards. I wanted to deal specifically with lower level hardware and IC chips. So in this case, you basically just shift in a byte, and if you daisy chain them, you can shift in several bytes and they'll just shift down to each one, and you can latch to read or write to the chip and effectively the outputs. So they were very good. There was some complications in wiring them, because there's just a lot of wires that go to them. There's 16 pins, and there's 2 of them. So you can imagine that there's at least 64 pins I was dealing with the wiring, and they can be a bit finicky. For example, one shift register, the 595 for the outputs, I have put on a power rail from the Arduino. I tied its ground to the other one, but I put its power rail on a separate power supply, and apparently that power supply was not supplying the proper 5 or at least 4.5 voltage. It was supplying around 3.8 volts, even though the little jumper is set to 5 volts and supposed to see 5 volts. So I didn't solve that like right away, if that was the issue or what was the issue. But they were not communicating properly, and one of them was like dead on all of its inputs. And I did a lot of troubleshooting and testing all the pins and replacing parts, and I realized that the problem was that they were getting different voltages, and so when I put them both on the same Arduino, then everything worked fine. Now I don't know if it was the difference of the voltage rails, that there were different supplies, or if it was just the voltage levels themselves. That would need further testing, but for now I got it to work by just supplying the same voltage lines. I was trying to reduce the amount of current that's being used from the Arduino or being supplied. So far that hasn't seemed to be an issue yet, so I can figure that out later. The other issue I had with the shift register is actually one of my breadboard rails were damaged and I had no idea, and it was the one that I was using from the QH of the first one, which is its output, to the serial input of the second 595 shift register. And so by jamming the like a breadboard wire into the hole that had its actual leg, so there's contact directly from leg to wire, then I went to just a different breadboard section and I routed properly, and then it was fine. So next, I have the load cell that is attached to the elevator car, and that is basically using a Wayne, excuse me if I'm not saying this right, but a Wayne strain, like a Wheatstone basically. It's using a Wheatstone bridge in the inside, which is just a series of 4 resistors with a connection, I believe, in between. And then it's checking the ratios of the resistors to find if there's any deflection. And then that's measured in millivolts that are sent to a dedicated IC that brings them up to a more readable scale for our microcontroller. So in this case, there are 4 through holes. 2 of them are bolted directly to the elevator car, while the 2 on the other end are pulled up by the tension of the cabling system. And so the elevator car is dangling directly by the load cell, which is not ideal. There should be a system where it's put in between the ropes and it's not actually supporting the weight per se. But for this prototype and proof of concept, it was more about getting that integrated chip working and the load cell working, and so it does work, and that was a key factor. So I did put in on the cabling system a tie off to the emergency rails on the sides, like physical rails, just to catch if there's a damage or drop. So also after that point, I I I'm sorry, I lost my train of thought. But anyway, so that's it for the load cell. Excuse me one second. Alright, so I'm back. So with the load cell, the issue was that I had wired the load cell into a sheath, a wire tape, a bundle of wires, and put it at the top. I lost track of which wire it was. And I had quite the time trying to figure out why it wasn't working, so I realized I mixed up the wire colors that belong to the Hall effect sensor. And that brings me to the Hall effect sensor, which is just mounted on the side of the elevator car, and then that is put in to one of the shift registers, and we read that for lining up to permanent magnets that are installed on the inside of the elevator shaft at key points such as lined up with the elevator floor for lining up. Next we have the DF mini player, which is just an audio player that uses an SD card, and that's when we can trigger sounds to play whatever we'd like. We have real-time clock, which uses I squared C. So we connect to that one and read the information, and we use that for our HMI packet and also for our logs. We have the HMI screen, which uses a shift leveler 3.3 volt logic because it is an ESP32. So in this case, I have a level shifter which shifts the logic of the I squared C bus to be from 5 volts down to 3.3 volts using some pull-up resistors and transistors. I did not wire this myself. I just bought a breakout board that handles that, and that seemed to be working fine. So the HMI screen itself is an Electro 7-inch digital advanced HMI display, which uses its own programming to display images based on information I send through I squared C transmission of a union data packet. Next, we have, which is a byte array. And then we have a 7-segment display. So one of the 595 shift registers is, the first one actually in the series, is connected to 4 7-segment displays in series, and sorry, in parallel. And it'll just update the same number to all 4, which is just our our binary representation of the floor number. If we increase more floors, we can change this to be a integrated circuit and multiple displays, and just drive that instead a different way instead of using a 595 shift register. And next we have buttons with LEDs. So each one of these buttons for the elevator cars actually have lights in them. So we have to handle the persistent logic where if a button is pressed, the light is retained. And there was some difficulties because it increases just the wires for each button, increasing the amount of effort. And so one of the issues is that I had ran all the power cables from the elevator up to the top, when in reality I could have actually just made a circuit board on the top of the elevator car that just put all the grounds and all the powers together, reducing the amount of wires going up and the thickness of the wires that I have to manage with the cable management system, by just effectively reducing the wires in half. And next I basically just use a bunch of breadboards. I have a couple breadboards that are partially empty due to refactoring. So this again is in the prototype stage, and it's more about getting the software running. All right, let's continue here to the electrical challenges. So I believe I did mention quite a possibly something in here. So the mixing up wires I did. So miswiring. So because there was just so many wires and I don't have a wire labeling machine or a lot of different colors, and I wasn't doing wiring things one at a time as I was going, I obviously, as mentioned, mixed up wiring, and I also mixed up on the little breadboard because the holes are really tiny, and when it's dark and I'm tired and it's nighttime, it's very hard to line it up. So lesson learned, make sure that I have the power off and I double triple check all the holes prior, because otherwise you might see a little bit of smoke, and that is what happened to I think one or two of the Adrenos I had. And then one broke just by the actual over plugging in the USB into the port, and it broke, so that would need to be resoldered on, but anyways, that was damaged that way too. And I mentioned the mixing the power supplies definitely was an issue, and there was some mechanical limitations. Some of the mechanical systems I wasn't able to get fully operational, so testing the program seemed more difficult when I didn't have an operating mechanical device to be able to line things up properly. All right, and now for the timeline reflection. So as you can tell, I overcommitted by putting too many things into this project, too many features, and trying to get too many things to happen at once. And also the fact that this relied heavily on mechanical components made it harder on the onset to be able to test the program. So realistically, what I should have done is at the bottom here, not add a new feature, add another feature, buy a component designed to fit it, and then add another feature again, because time was wasted that way. And then also, I could have developed the system where I had actually used the like dummy values and just printing to see everything was working in the logic, and then plug in those things afterwards. But I was building this and learning, so it was definitely a learning curve, and I did put too much emphasis on the HMI screen, and now I do have an HMI system that I can refactor for different applications. There was a lot of time invested that could have been used for the actual delta elevation system. So I did not give the appropriate time to the latent needs of my customer, and unfortunately that hindered the progress of the elevation system. Next, we're going to get into the coding with a video I pre-recorded, so let's get into that. Thank you. So here we have the software for the delta elevation microcontroller. There's a lot going on here, and I'm sure there's going to be much room for improvement. I did try to comment a lot of things. So we use the SPI library for the SD cards and shift registers, and for other future components, we use the wire library for the I2C. This one's for the music player. This is the load cell. This one is to help with the music player because I didn't want to use RxTX because we use serial print. We have for the servo, we have for the timer, which is for the power loss detection. That's just a timer to run and check to see if there's a power loss every like 10 milliseconds. And then we have the library for writing to the SD card. Next, I just use a lot of defines to try to save some space. So we're just defining some baud rates and the address of the HMI screen. This is a chip select for the SD card. Some error codes, some log types. This way, while programming, we know what these numbers mean. These are for the sound player, sound effects. This needs to be refactored. There's some naming convention issues there. These are for the statuses for the elevator, which is a state machine. And same with the doors, which also has a state machine. We can use some debugging to limit the amount of prints being set. Sorry, that's my... There we go. Here we have the pins for the power cap, which is just a capacitor, doing load cell pins here for reading that. We have for the latch pin for the shift register for the outputs, servo pin, MP3 player pin. So we're basically using most of the pins, and some others are defined in other areas. So that's why we're using the shift register. So these are for the interrupts. And now we have some specific settings for the floors, which are used for telling what floor we're at, what was the last floor, what's our target floor, how many floors are in this system. This is a constant, so this will be used depending on the floor system. And this is for when we're approaching. It's used basically to help ramp the motor and slow it down when we're approaching alignment. Next, we have, this is for the digital display. This is just for the counter. So this is 1, this is 2, this is 3 for each floor. So this is hard-coded. And this one is to store the data we're getting in, the data we're getting out, the last data we had for making comparison. And we use some states to confirm for debouncing whether the inputs have stabilized or if they're flickering due to static. We have some information here for the motor. So these ones are coefficients. So basically, because there's a weighted car and a counterweight, and the nature of the motor, it may not always run at the same speed in each direction. So this program has a future scope. It does not implement this yet, but what I would like to do in the future is look at the load cell and previous timing it took to travel between floors and adjust these coefficients based on that to provide a more uniform travel speed. And this is just to say that the ramping speed is done and it's reached full speed. This is the sample time to help get the duration that we're going to be ramping as a, we use it basically to get a percentage. And this is the lowest amount the motor can run. It's really actually at 72, but I noticed that 88 had a bit more torque and was more reliable. Next, we have some various system settings here. So these are just to say if there is a failure, if there's a power loss issue, if we're checking the initial capacitor, so basically just charging at the start. If we're going to be using sound effects, like if we're going to be triggering sound and identify the sound. This is for lining up the car at the starting. So I think I'm not sure if this one is in use. You know what? This one I had changed the way I did it, so that's no longer needed. Okay, and so this you can set the various debugging level you need. Wire speed clock was a variable. It's set as a define now. That could go up at the top. This is if we want to just disable the sound. We don't necessarily need to have sound playing, so that can be turned off if it's bothersome. This could be an external button. Anyways, and then we have some load cell values, debouncing information, some specific information for the time. This one tells you if the real-time clock has been accessed so that we're using the correct information. If not, we need to consider what, we do consider what information we'd be using for the time. For example, writing to the SD card. This is used for the service mode. It's just for basically just keeping track of when service mode was pressed and the speeds and various stuff for moving to the first floor. This is just information for the SD card saying whether it's ready or not, if the last log was flushed or not, the current index that we're adding to the logs, how often are we going to actually write. Next we have for the boarding sequence, we have the speeds for the doors, how long the doors will remain open before closing, other specific information. This is the information here for the floor data. This masks are used to be able to get the proper information for the shift register. So if a shift register is changed around in its order or the wiring, these are the ones that need to be addressed. And these are some variables that are received from here, and these are stored in here. And then later they're actually stored into a structure down here called floor data, which is right here. So anyways, this one can be refactored, I think. And then we have the status of the door. So this is for the sensor on the door to see if the beam was broken, infrared sensor. So that's just to kind of keep track of if those are triggered. And again, it's the same convention of where is the bit in the shift register input, the 165 shift register. And now we have a series of structured data which is used to read different states of the machine, and all of these structures are actually embedded inside of this union. So this union basically takes a struct and it pairs it with a byte, with the bytes that belong to this. So this way we know the actual size of the bytes of the HMI package that we'll be sending to the HMI, and we're able to access the bytes via this one here. So we use this one, and we use this accessor, and we are able to effectively get information in these different structs. And so we use that to control our system and to transmit data. And part of the data that we will be looking at in there is the call status of a specific floor, the position sensor, if that's been active or not, the limit switch high or low. This one actually is more purposeful if we have a position sensor on each floor. Currently we have one per car, so we would be just updating that right now by using the one on the car and the last known limit switch that's been active. And we'll use that basically in the targeting floor to tell if it's been active. But essentially we should have a position sensor on each floor. I was just trying to reduce some overall costs and redundancy. And here we have some basic system data. This is that Hall effect test sensor I was talking about, which belongs to the car. And if the system is in a fault or an e-stop, and using the primary state machine, what's the state status that's being used, and if there's an error, what is that, and what's the current motor speed and direction. And all this is sent to the HMI screen and updated. Now we have event logs, which are used to be able to log the just a message basically of when something happens. For example, if the e-stop is pressed, we can log that, or depressed, and we log it in 20 characters. And the last character is actually used for a null terminator. So we have 19 characters to be able to write our message. And we're able to use just a numbering system to identify the type of log that is being generated, and we use a timestamp. And now, because there's not a lot of room on this, I originally had this as 100 or 200, but as the program inflated or got larger, I was not able to use such a high number for this. So we only use 15, and we periodically dump it. Unfortunately, that is a side effect of this type of system. With some refactoring and possibly an additional EEPROM chip or some other, or just writing to the SD card more frequently, we might be able to effectively get this to work out better. We can also, instead of a message, update this to use a digit, and then in that document someone just references in the spreadsheet what that is. So using an Excel document and then having a cell say, if it's number 1, go to the other sheet and populate with that corresponding message. So this can be reduced, and if we do reduce that, we can effectively increase this one here by just changing this to an unsigned byte, and then we just have something like that. Okay, so for now the system works like this, so that's fine. So we store that data for each floor, and here is the as I said, the information for transmitting. Now these are the floor stacks and elevator stacks. So this is basically just first come first serve, who pressed the button, and that will be the one that's serviced based on direction and location though. So there are some specifics. For example, if we're on the first floor and somebody on the third floor pressed the button first and someone on the second floor pressed the button, it'll go to the third floor first. But if this person on the second floor pressed it first and the one on the third floor pressed it next, it actually will just go to the second floor since they were priority, and it will switch into the down direction and it'll just pick up everybody along the way, and the third person will have to wait. But everybody who's in the stack who is the second floor or less, you can imagine if this was 20 stories and it was 15, then anybody under 15 would also be picked up, and that person who called at the top would essentially be shifted over into the stack and be the next priority. So I tried to balance directional sweeping with prioritizing first in, first out without having too much random movement. Now we come into the area of the functions. This one's used to transmit the HMI data. We're basically doing it 30 frames per second, targeting the outlined HMI address that's set in the wire.begin on the other device, and that one we use we set the HMI address. So it's already set. So I have it wired hard-coded in here at the top in the define. We write our information that we need here. So we are using the bytes and the size of information of the packet. And these two, this is the power of the union. It's able to actually take the bytes of the HMI packet into one data type. So we can easily send it. This one's reduced. This could probably be increased. I just put it as safe limit. That could require some additional attention. And here we just handle error detection if it failed or succeeded. Okay, next we have initializing the SD card. I will get into this. This is starting to take a little bit longer than I expected. So anyways, we just set the pin and we write to it and we check if it worked or not. Then we have this for adding the logs. So here we get the time that was used by a real-time clock, and then if it wasn't used by the real-time clock, we do not use this information here. We just use millis, and essentially we're just adding a timestamp and creating a log like in one of the elements there that we're selecting here. So we basically increase the element we're doing each time by 1, and then by the time we get to the next one, we just repopulate the information with the message that we're sending, which is up here, and with the type. And at that point, when we are over 25, which are over or equal to 25, which I believe that was now changed to 15. So there's a little error that's found. So when we get to 15, we basically write it and restart the index. Now this should be tied into a variable so that that issue is not, that just fix is not there. Okay, so next we write the log to the SD. So this actually just opens a file stream and then uses a series of prints, a method that belongs to the file data type, and we just print right into the file. And we close the file when we're done. And then we can also flush, which just means that when it's full, when the time is reached, the hour or whatever we set out, it will just write basically to the SD and restart our logging back to 0. So if it's a slow day, it will still log. There should be something here. So if there actually is a log, so if it's sitting at 0, it's not. It's just going to ignore it. It's not going to be writing nothing. And then here we read from the real-time clock. We're basically just collecting the information from the clock and storing that into time variables and then breaking that down into a displayable time. Essentially, it needs to be reconverted to a usable time here that we can add or subtract information from. Okay, and then this is just to get the lifetime. So a lot of this is reused on the HMI screen to be able to display the time. And this might be needed for timestamps and future scope. Okay, and this is just us starting the I² bus. And now we have here if the E-stop is pressed. In this case, if the E-stop is pressed, it's going to go to emergency mode and it's going to log that. Otherwise, if it's pressed again, it will turn off the E-stop and set the system back into regular operating mode that it was found in. And it will also send a sound to play. Alright, so continuing on here, we have a similar system for service mode press. In this case, this one is just used to go down to the first floor. This should be expanded to allow any floor selection and just a specific use of maybe buttons for how you're going to go to which floor. The elevator I've been in before in a place that I used to work at, you would just hold the buttons and it would go when it's in service mode when the key is activated. Alright, and next we have a service mode. So this one is basically used, I kind of forgot here which one, it just clears the floors. It has, so this is just to implement this one where it basically just goes to the first floor, closes the doors, moves the motor, just kind of more of a physical thing, like it actually does it. And there are some specific use cases here where it'll go back to boarding mode if it was already boarding. So trying to retain some information. So basically, there needs to be a few more statements here to be able to really tell when it's interrupted a system. So for example, if it's boarding, we want to make sure that it goes back to finishing that. Otherwise, it could potentially just keep people stuck on the elevator. And then this is just for targeting the motor speeds and moving it into position to the first floor. Okay, so we'll probably just move along a little quicker here. So this is for the shift registers. So basically, we're just pulsing the load pin to get a snapshot of what's going on the 165. We're beginning the transaction. We can probably increase that speed there. And we're dividing, because there's two chips, we're just using high byte and low byte. And essentially, it's 8 bits each. So if you have more, you'd actually either use bitwise operations to divide it up, or you could use high byte and low byte and just split into partitions. Okay, and then we get the information, read it here, and we're also sending our outputs to the actual 595 chips for lighting up our buttons and for the 7-segment display. One actually is for the 7-segment display. I believe it's this out low. So anyways, then we have some debouncing here to just make sure that we're not reading it too fast and getting flicker. And then we apply this to allow for persistent floor state. So if someone pushes a button, you'd like for the button to be lit up and stay lit up. So that's what that's doing. And this just updates the limit switches using those masks and the sensor state on the door using those masks. And we basically say here if the current floor is over 0, which means the system is actually running, we're going to add the current floor to be put into the output for the 7-segment display. The reason why we have this is just in case the system is initialized with a 0, we don't want to be trying to access our floor display array with essentially a -1. Okay, and then some debugging printing if needed to see what's happening. And then this is information that just uses the bitwise operation and the mask to be able to say if the mask, which will have one bit that says 1 and everything else is 0, and this one both are high. So it's just going to basically say the only one that's high is the location for this bit, and then it has to be actually high for my reading. And if that's the case, I just set true or false the information in the HMI packet. And that's what we use to control our programming flow. So the same kind of goes on here with the elevator buttons. This one actually was the limit switches. This is for the elevator buttons, whether it's on the floor or in the car. And this one here is for the 3 door sensors to sense if somebody is obstructing the door. This sets up our mini player with a default maximum value, which seems a little high. So you can kind of change that there. This could be a global variable. This way it's just more easily accessible. Okay, and then here we have the initialize the load cell. So if the load cell is found, we set the scale. We're just using raw units. We're not calibrating yet, so that is future scope. But for now, I think that's fine. There's a variable at the top which hard codes the amount that's needed, and we do it over an average of 50 readings to try to get a better stabilized 0. Next, we actually read the load cell, so this is used throughout the program. This is just for the setup phase. We initialize the servo. That's kind of obvious. This one is also the servo for the door wasn't fully implemented yet. So this one basically just writes to it, gets it to the center position, and waits a second. So this actually is better for when we're using a non-continuous 180-degree servo or 120-degree servo, or whatever the degrees happen to be. But I think the system is going to be using a continuous servo, so a lot of this code might not be necessary. But it's a good initialization check, anyways. This one's just for moving the motor, specifically moving up or down, just making sure that the other direction is turned off so there's no issue, and using the coefficient of the up. And we just give it the direction and turn it on, and it will basically take care of the speed. And I believe we use this in some areas, and in a lot of areas where for testing purposes it's simplified to just use the minimum motor speed. This one just checks the power loss, adds a log, actually runs the e-stop, writes to the SD card. That's all the logs that are in the system, transmits to the HMI like a final packet, and plays a power loss sound. At this point, there's the rails on the power of the Arduino are no longer 5 volts, and they're likely around 4.5 volts and dropping. However, I do use a 2.5 farad 5 volt supercapacitor on the power and ground rail, and that actually slows down the decay by feeding back voltage into the system, and by power. By that reasoning, this one has a little bit of time to run this last ditch effort to save information. So as the elevator system gets more complex, mechanical stops and other critical safety systems will be employed to apply effective braking. Power loss, this one just charges. So basically just reads the cap. If the cap's over 100, that means that the power loss is happening. If it's under 920, it just means there's not enough power in the cap. So essentially, when we're charging our capacitor to 920, we're basically saying we want it to be about 90-something% of the overall power of the board. And since the power of the board is 5 volts, that gives us 4.6 volts. So this amount is actually always compared to the voltage on the board. Now, if our capacitor is stored with, remember this isn't the super capacitor, it's a different smaller capacitor. If it stores 4.5 volts and our device has 5 volts, we're at 90%. But if our device drops to, say, 4 volts, our voltage on the capacitor is actually over the voltage reference inside the microcontroller. And so this actual reference is going to then tell us we have 100% on that analog pin. And that 100% basically means we have more voltage, and that's a problem if our voltage is only 4.5. So that's when it starts to trigger the power loss detection and set the state. So we can, in emergency, write to EEPROM. Right now we're not doing that. We're just writing to that SD card. So this is a little bit older. We've updated the technology to SD card, but this could still be employed, but code would need to be written for that. It's not necessary. And also we could update the HMI with a specific HMI data that may or may not be a packet. Right now that doesn't happen, so it just returns. So that's future scoped. Okay, so next we just pre-charge the capacitor at the very start of the program. Again, I'm just trying to speed this up. And then here, this is just initializing what information is needed for our system to run and what we want to send to the HMI at the beginning. And here we get to our setup, where we set up the serial, we set up the music player, and then we can set to play sounds along the way to kind of have an audio cue of what's happening. And we charge the capacitor. We set our pins, we write them low. We don't want the motors moving, so we write them low as soon as we can. We write the shift registers high as soon as we can. We set the pin cap input, and then we just do some reading. So it just sets up for when reading will be needed. And then here we set our interrupt. So we're checking if the interrupt pin's valid. If the microcontroller's been changed and it doesn't support this pin, we need to know that. And in this case, it gets stuck in a while loop because e-stop is a critical system. It should not run without the e-stop. So in this case, I think a new microcontroller will need to be used to check if that is safe. And then a similar is done here with the service input, but since it's not critical, we don't worry about that and the system can still run. We start the SPI here. We initialize the SD card, check if it's ready. Now we can run an if statement where if it's not ready, we might notify the user. So here we start the wire again. And this is for the I2C. We initialize the I2C. We just play some sounds. We check for the real-time clock. We initialize the servo. We send an initial transmission if needed. We tear the load cell and see if it was found and properly teared. Now, there was some issues with the real-time clock, so I had put if the time wasn't found to try again. And this may be fixed by not allowing the HMI to address it, and for only this master device to pull the RTC, and for the time to be sent through the HMI data packet instead of the HMI trying to get it itself. And this sets our initial states, which theoretically should actually be declared. After that should be declared after that. I'm not sure if that would transmit anything, but I'm sure it would just transmit blank and it would have been caught in the loop. So in the loop, we always update our time. At this point, we check if there's an e-stop, and we don't do anything unless the e-stop has been cleared. When there is no e-stop, we got our inputs, we transmit to our screen, and we check if we need to write anything to the screen. Anything to the SD card. At this point, we just triggering some information here if needed about the limit switch states. And then here we just check if any sound is required to play, and if so, it needs to be like what sound is it. So sounds are just using numbers, so we just check if it's true, which means it's not 0, and then we use that number to find the corresponding file, which is always 4 digits, for example 0001.mp3, and it's in an mp3 folder. Okay, and that brings us to our master state. This is a state machine, so it just uses a case switch to be able to identify specific states. So in the initialization, we're basically just lining up the elevator car by driving the elevator car down. So we always initialize the program with -1. So always drive the motor down, just making sure, this is a bit redundant, but just whenever we're moving the motor in a direction, turning the opposite direction off. And then we just move down, and we're moving down until the basement position is set. So as it loops through the program, it will keep coming in here and being -1 and checking this. Once this is actually pressed, there's a physical button, an electrical stop in the basement that the elevator car pushes into. And once it pushes into that, we're at the bottom. And at this point, we now set this to 1. And we start to drive the elevator in the, I guess it could be a 0, but we start to drive the elevator in the up direction, and now we use that while it's driving in the up direction. And remember, this is no longer going to run. So while this is running, we're just checking the Hall effect sensor for the first floor to be triggered. So because we're already in the basement, we know the first trigger of the Hall effect sensors has to be the first floor. So at that point, we put ourselves into standby mode. Now this is the e-stop, which just basically prints e-stop. Now I believe in the actual up at the top, this one never gets triggered because we used we used the else statement. So it does just stay in here, but we could essentially just else where it skips all the way to right before the state machine and allow it to go into the state machine. So two different systems here, but essentially just in case there's a change to that, this will automatically catch it. Okay, so for the standby mode, we're actually just going to run where did I put it? Somewhere. I'm just going to run this here, and essentially what this does is just check the call stack if there's anything active. So it will check it'll check first the call stack for the elevator, and then it'll switch and check for the floor, and if it finds anything, it will go to system is responding. Okay, and then as system is responding, it will run this function. Let's see if we can find that here, responding. Okay, so in this case here, we just check the direction of the elevator, which direction it's going. If the elevator is going up, we're actually going to be servicing the elevator stack, which is all the buttons inside the elevator. We'll be completely ignoring any of the calls of anybody else, because this is a single button elevator system where each floor has a button for just specifying going down. Now, this could be updated later if there's multi-directional, if multi-direction is allowed. And so then if it's going down, we just read the stack floor. So now the difference is that when we're going up, we're just servicing only those in this stack and opening the door for those. But when we're going down, we will actually be servicing this a little bit differently. We're basically saying that if the if we're at a location and we're going down, we'll just be checking both the elevator stack and the call floor stack, both stacks, to service anything that's along the way. You know, of course, if anybody pushed a button and they're wanting to go to the second floor from inside the elevator instead of the first floor, or if anybody is on one of those floors in between, then basically we want to pick them up also. So we need to constantly get the elevator location, and if it's not reached its current location, it will actually allow the traveling, which is just controlling the motors and moving things around safely. The elevator location is just simply checking the limit switches of each floor and deciding whether they are high or low, and if so, updating the approach floor, which is just used for positioning and easing the motor. And at this point, we add a log specifying we've arrived at that floor, and we stop the motor from moving, and we set ourselves to align car. And align car basically is just lining up using the sensor, just making sure that the sensor is triggered in a way that allows the car to be lined up correctly using our direction here, and driving it up properly using the Hall effect sensor down here. So this block code kind of tripped me up, made me feel like it was, but the indentation here is different. Okay, so this is fine. This is all one unit. Let's just, there we go. So yeah, okay. So that happens, and then when we go back to, let's go back to our state machine. Actually, let's check out the boarding. So for a boarding sequence, I actually just put various sequences here. So the first sequence is opening the doors, which essentially just plays doors opening, writes the servo to start opening at the right proper orientation and set speed, and updates the HMI status to the doors opening. Then it sets the boarding sequence to the second one. So it just initiates it. The second one actually first checks if the door sensor is active, which is the one that's used to see if it's fully open. So it's a limit switch. And then at that point, it will turn off the servo, set the doors to open. It will check the time for when it's officially been opened, and it'll start the next sequence, which basically uses a timer to make sure it doesn't close it until the time is up. And at this point, if any of the sensors are actually not hit and the time is up, then we'll start to close the door. But if something is hit, we're actually going to change and update the door time and give an additional 4 seconds. This could be fine-tuned, but for now it seems to be a good enough safety system. And when that case is true and nothing is in the way, no obstruction, and the doors are finally closed, we move on to the fourth one, which is just basically checking the other door sensor for when it's closed, writing it as closed, turning off the servo, updating it to close, and then setting the system into service mode or standby. So service mode just means it's going to return to service mode if that was operated with a key switch or whatever. Otherwise, it's just going to go to standby, which then will start scanning those packets and starting to decide which floor to go to. So for that case, we have covered the state machine so far with the e-stop. We had covered it with the initialization for starting the car, the boarding, the system fault. This one just, oh yeah, we had discussed this here also. Actually no, I don't think we did. So in this one, it actually checks the load cell. Make sure that the load cell is in the safe threshold of 10% underneath the maximum to be able to start again. Otherwise, they'll stay in a fault. So right now, the primary purpose of this fault is actually just if the weight is too much. And you can see that here, I believe I used to have the weight check in here, but I actually just switched the weight check to be done periodically or frequently. And so this ends up getting interrupted, and then that's where we're trying to recover if we're at this point where we're opening and closing the doors. Okay, so we don't want to trap folks in the elevator. And that basically is a high overview of the system. There's a lot more information declared in here. Like for example, we do have functions to add to the stack. And so when we add to the stack, we're just kind of making sure it's not already added and returning where it was added in the location. We do have things removed. So we remove a call after it's been serviced. We do want to reorder it. And we do have checking the call stack and kind of iterating through that. So every time we check the call stack, we just reorder it. And the reordering is basically just removing anything that is empty. So, if it's a 0, then it will basically reshuffle that and condense it. It's still keeping the actual order of priority. And then in the standby mode here, I'm not sure if we covered this, but basically this one just checks just checks if the floor and the stack returned is a floor that we need to go to. If it's not, there's no calls, it's 0, it's just going to do nothing. At this point, we can implement some other functions like maintenance or different things for the system to be able to do. At that point, if there is something, it's just going to set itself to respond and update the target floor to be the floor it found in this call stack check, and then it'll start, well, basically the responding will start to take care of that. And then here we have, if we change direction here, we're just doing another call stack. I don't think that this one is fully in use yet. So it's just another way of changing the system. So we'll just kind of not yet implemented. And we kind of do things a more hands-on approach. But essentially we would want to be changing the direction and doing some checks and reordering here. So just need to continue with that. All right, and then I believe that brings us to most of the information that covers this system. And yeah, okay. And then here is just some information for how we ramp the speed and how we use the time difference for changing the speed when we're approaching the floor. And this is just built into the travel system for the initial driving, like moving. And the other end, the slowing down, is more so in the aligning car portion. So this portion is just using that same principle for using a set time to get a percentage to offset the minimum motor speed. Here, the motor's lowest RPM. Okay, and so that brings us to the end, conclusion of this portion of the code. The other portion is the HMI, which I will not be getting into in this demonstration, but I hope to get into it further in another video. Thanks again for watching. I know this was a lengthy video. There's quite a bit of code here, but I was hoping to give you a good detailed analysis of what exactly is happening here and why it is 1,500 lines of code. All right, and this basically concludes the delta elevation overview. There's a lot more to go into with the HMI screen, but I'll leave that for another video, and I hope you enjoyed this. More mechanical information will be shared in another video where I demonstrate it, but for the purposes of keeping this slim, I wanted to talk more about this system than displaying the actual prototype design. So stick around, continue to my YouTube, which is www.cornerpi.com, and there'll be more information to follow. Thank you.